Ari's direction. Spent some time in Leuven in Belgium, and he's now back in England at the University of Manchester. We're happy to have him here at the same time with this induction of the new lecturers happens.
Thank you for the introduction. I hope that the title has been enticing enough. Clearly, it's enticed a big audience, particularly for this room. So I'll just first say that this is energy-preserving spectral methods in the real line. That's what's going to attract the TCS crowd, whose analysis strays into the complex plane, attracting the CAT crowd. And it's joined with Ari Solis and one of his PhD students, Karen Long. He's sat there. So you can tell me if anything's wrong. Ari, you're done. Please do. Okay, so let's motivate the work. Consider some time-dependent PDEs. So we've got a solution which depends on a time variable and a space variable which is defined on the real line. Consider familiar PDEs like the diffusion equation, where we would assume that the diffusion coefficient is positive or negative. Semi-classical Schrödinger equation, small parameter epsilon, and a real potential V. Nonlinear vector equation, satisfying this condition here. What's the common property between these three systems? They're rather different, but if the initial conditions are an L2 function, then the L2 norm will be non-increasing. They have an L2 stability property. That does depend on these conditions that are put here on the right. And the L2 stability it essentially follows from integration by parts. So this is just expressing what the derivative of the L2 norm is in a simpler fashion. And for the diffusion equation, if you plug in what du by dt is into the expression, and then integrate by parts to get from this line to the next, the assumption that A was positive gives you that derivative must be non-positive. And for the Schrödinger equation, it's a similar trick. It's integration by parts on just one of the derivatives in the passing part. Because there's only real terms here being multiplied by I, and we only care about the real part, the derivative is 0. This is all elementary stuff. But for the Schrödinger equation in particular, this is a very important property. It's in the Born interpretation of quantum mechanics, the square of the solution is a probability density distribution. So this integral must remain constant. It must remain 1 for all time. It's an essential part of the equation. So we would like our numerical solutions to respect that. Okay, so if we were to do a spatial discretization, for example, finite difference, finite elements, pseudo-spectral, try and be as broad and conceptual as possible, the nonlinear transport equation I mentioned would get converted a PDE into an ODE, an ODE where we're evolving it as vectors, evolving with time. And there will be a matrix D which is discretized the derivative, depending on how the discretization works, and the nonlinear transport term would have been discretized as well. What about the L2 norm of this discrete solution, this numerical solution? Well, just an elementary calculation. Just expand out what this derivative of a norm is. And depending on how you carefully discretize this transport term using the assumptions we had on it, this would be non-positive. And so what we would like is that this be 0 if we're going to be respecting the property, the L2 stability property. So if D were a skew Hermitian matrix, this would be 0. And it sort of is saying that that we're mimicking the integration by parts that exists. So our discrete equations would be mimicking integration by parts if the differentiation matrix is skew Hermitian. And so it was Ari Uselas who started a program, you might call it, in 2013, 2014, so emphasizing the importance of making a differentiation matrix skew Hermitian or skew symmetric, and that it makes it stable by design spatial discretization. And the Lax equivalence theorem says that stability and consistency is equivalent to convergence, so stability should not be an afterthought. It's essential. And this Born interpretation of quantum mechanics says, yeah, it's important for energy conservation if you want your numerical solutions to have probability distributions. So let's look at some differentiation matrices. This is the one that people might be most familiar with. This is just the second order finite differences for, this is a very basic discretization. It's skew symmetric. That was easy enough. Looking good. However, one of the interesting results of our ESL was that this is actually the highest order skew symmetric differentiation matrix you can make for a finite difference method on an equal space grid. So, if you want to get higher than second order, you have to get away from equal space grids. And with some joint work with Ernst Heyer, they showed that if you can use special grids, but it gets quite complicated. And this is the joy and the pain of skew symmetry, as Arya put it. Okay. Now, let's suppose we want to approximate the solution to the Schrödinger equation using a spectral method. So we would take a basis, which we'll denote phi n, square integral functions on the real line, and we represent our solution as an expansion in that basis. Then the coefficients of that expansion, which we might represent in a vector u of t, an infinite vector u of t, will satisfy an infinite dimensional ODE, where D and V are infinite dimensional matrices encoding the derivative and multiplication by the potential V. So this defines the matrices D and V in the discretization. And we want to ask, how can we ensure that D is skew symmetric? That's the main gist. So the most famous spectral method is the Fourier spectral method. It's quite beautiful the way that it works. It's very effective. An orthonormal basis. And the differentiation matrix, easily enough, is skew symmetric. The derivative of the constant function is 0, the derivative of the cos is the sine, the derivative of the sine is the cos, the derivative of the cos is minus the sine, and so on. It's a banded skew symmetric differentiation matrix. However, it's only for periodic boundary conditions. These differential equations we're talking about were naturally posed on the real line. Now, what about square integral functions on the real line? The world isn't periodic. Why should we start assuming it just because Fourier spectral methods work so well? They're going to have, for example, this stable by design property because of the skew symmetric differentiation matrix. Okay, on the real line, yes. They have Hermite functions. They're a Gaussian function multiplied by the Hermite polynomials with a normalizing factor. It's an orthonormal basis on the real line. They're uniformly bounded and smooth. They're eigenfunctions of the Fourier transform. They're quite beautiful functions. And some people use them for numerical methods. And these, it's well known that these satisfy this relationship. The derivatives have a very short recurrence. So their differentiation matrix is skew Hermitian, skew symmetric, and tridiagonal. Let's think about alternatives to Hermite. Not necessarily always advisable to use Hermite spectral methods. So our desiderata that Arya and I set out couple of years ago, or maybe 2017, characterized all systems of functions, phi n, satisfying this very short recurrence for the derivatives, these two lines. And what it means is that the basis has a skew Hermitian tridiagonal, an irreducible differentiation matrix. It's irreducible because these off-diagonal entries Pn will be non-zero. That's just an assumption that it might be quite a strong assumption that this is a tridiagonal differentiation matrix. We also would quite like them to be orthonormal. If we're going to have a discrete property about the coefficients, about this norm being preserved, it should match the norm of the function, and that's only going to happen if it's an orthonormal basis. And ideally, these are desiderata, these are things that these things we desire, but it might not be possible. We'd like a fast algorithm to actually compute expansion coefficients. For Fourier series, you can approximate expansion coefficients using the fast Fourier transform. That's the ideal situation. Maybe we could mimic that with some new bases we find. And actually, we found some characterization. A basis of functions in L2 on the real line satisfies this tridiagonal skew Hermitian differentiation relation if and only if your functions are what here is it's a Fourier transform of some orthonormal polynomials, Pn, where there are some mild assumptions on the measure with respect to which they're orthogonal. Some function g, which decays superalgebraically and is in an L2 function. And then there's some little parameters, theta n. But this is all the functions that satisfy this relationship. And if you really want to make sure everything's real, you can make some simple conditions on G and theta n. So all you need to do is pick your favorite orthonormal polynomial system, pick a G, then the Fourier transform of that will be a system with a skew Hermitian differentiation matrix, tridiagonal. So I'll quickly sketch some of the ideas as to why it works. So we have this ansatz here. Assume that our function is of the form of this ansatz, where the Pn's are orthonormal polynomials, which implies this recurrence relation for those polynomials, a symmetric one, that's equivalent to orthonormality. If you differentiate this under the integral sign, so to speak, the only term that depends on x is this guy. So all it does is add an I psi term there. And so you can see how then the three-term recurrence then comes into play inside the integral, and essentially the Fourier transform turns differentiation into multiplication by I psi. And the reverse uses Favard's theorem for orthogonal polynomials, invertibility of the Fourier transform, some heavy lifting, but I don't want to get into the details of this. Just know that two of your favorite things are involved in this theorem, and that's orthogonal polynomials and the Fourier transform. Sorry if I don't speak for you, but they certainly are two of my favorite things. Okay, let's take a family of polynomials. Let's take normalized Legendre polynomials. Satisfy this orthonormality relation. If you take the Fourier transform and look on DLMF, you're going to find that they are spherical Bessel functions. So these functions, which have a simple, they're denoted as Jn, as the spherical Bessel functions, they satisfy this sparse differentiation relation. And these coefficients come directly from recurrence coefficients for Legendre polynomials. So if you built a spectral method out of spherical Bessel functions, it would be stable by design, and it would have a tridiagonal differentiation matrix. Not necessarily an advisable thing for a spectral method, I don't know, but it would have those properties. And what about the Hermite functions? It was already known they had a tridiagonal differentiation relation. This relationship was already known. How does it fit into our framework? Well, the Hermite functions are eigenfunctions of the Fourier transform. And the functions that Arya and I have characterized are Fourier transforms of orthogonal polynomials. So they're a fixed point of our correspondence between orthonormal systems and orthogonal polynomials. Okay, so we have this formula, this ansatz for some new special functions. How can we tell if it's orthogonal? Is it easy? Well, actually, Parsifal's theorem says that the Fourier transform is unitary; it preserves the inner product. So if our new basis phi m is just the Fourier transform of some weighted orthogonal polynomials, then the inner product is preserved. So these phi m's are orthogonal if and only if the pn's are orthogonal with respect to g squared. So our characterization also made it really easy to tell whether it was going to be orthogonal or not. So that these systems are orthogonal on the real line if and only if P is orthogonal. The orthogonal polynomials it's derived from are orthogonal with respect to the G that we've used in the formula. So it's a special choice of G which will make it an orthogonal system. So just to summarize that, if all orthonormal systems with a tridiagonal skew-Hermitian irreducible differentiation matrix can be expressed in this form. So this W to the half is a special choice of G, it's the square root of the weight for the orthogonal polynomials Pn. Perhaps I've put here clearly in not necessarily clear to everyone, but if the polynomials are dense in their respective space, and that the systems derived from this formula will be dense in a Paley-Wiener space based on the support of the weight. So in our early example, we took the Fourier transform of Legendre polynomials. We've got spherical Bessel functions. They're orthogonal on R, and they are dense in the Paley-Wiener space where the Fourier transforms are supported on -1. So this Paley-Wiener space stuff, what it tells us is that it's got band-limited functions. So that stuff might be of interest to signal processing researchers, we don't know. We've not delved too much into that. But it also tells us that the basis that we generate from this formula, it won't be complete unless these polynomials are orthogonal on a weight on the whole real line. So you can't. Yeah, so it's not going to be a good idea to use spherical Bessel functions because they're band limited. If you were to use it in a spectral method, it would only be useful if you expect the solution to be band limited. I don't know whether that's necessarily the case. Okay, let's take another set of polynomials. Laguerre polynomials is probably the next thing on everyone's list. Classic polynomial families. Orthogonal polynomial families. So they're orthogonal with respect to the exponential weight on the half-line. You scour DLMF, you'll be able to work out what the Fourier transform of these Laguerre polynomials times by the square root of their weight. They're actually rational functions. And as I said, they will span a Paley-Wiener space based on whose Fourier transforms are in the support of the measure, which is only the half-line. So if you want to make it complete, you just take n to be in the whole of z. And it turns out this is a rediscovery of some functions which has a very long history. So it goes back to Malmquist and Takanaka. So we call them Malmquist-Takanaka functions. But even Wiener discussed them in some signal processing book in 1947. In terms of approximation theory, such as Higgins, Weidemann, who's in the audience, one of the organizers, he's studied quite a bit these functions. So that was when we realized we'd started to make a real rediscovery of some family, was when someone forwarded a paper verbatim on it to us. Researchers in rational orthogonal functions, such as Boltail, studied these functions. And in the context of spectral methods, the most famous name is probably Christoph. Sometimes these are called the Christoph functions. But they have been used with some success for things, integral systems like KdV, Brussinesque, nonlinear Schrödinger, on the real line. This basis has been used, so we've rediscovered it through our characterization. And Andre Peterman himself has used them in certain situations. They have some nice properties for spectral methods, actually. So we have this tridiagonal skew emission differentiation matrix relation, but also there are some sparse relations for multiplication. So they deal very well with nonlinear problems. And this was noted by Christoph first. So you could some people do call them Christoph functions, but we don't. You could argue that if you're interested. Okay, but let's analyze these Malmquist-Takarabe functions a bit more. MT functions for short. They involve this quotient here. If x is real, and this actually has norm 1. So these functions, they're like this. They've got something with norm 1 in there. So if we set this term to be e to the I theta, which corresponds to x being tan theta over 2, if you change variables in this way, you find that the expansion coefficients of a function in this basis, they're actually classical Fourier coefficients of a modified function. So you just change variables from x to theta, work out what happens with all the Jacobians. These coefficients of functions on the whole real line can be reduced to a periodized function on the periodic interval. So this function, which might be decaying at infinity, this variable transformation here just squishes it all up to something which has all its derivatives 0 at plus or minus pi. This also reveals, by cancelling out the absolute value here, this also reveals that the absolute value of these Malmquist-Takarabe functions is quite simple. It's decay like 1 over x. And this is what they look like. They have this envelope, this 1 over square root 1 plus 4x squared, this dotted line. And they're quite nice looking functions, but they're complex, of course. You can make real versions. I think Christoph himself, in his original paper on them, made real versions. Okay, so Arya and I later asked ourselves, okay, one of the nice properties about Malmquist-Takarabe is that you can compute coefficients using the FFT, because their coefficients are actually classical Fourier coefficients. So we asked ourselves, are there any other bases where we could do this? The FFT is probably the best thing in the world, computationally speaking. Probably over the top, but so let's say, okay, say we've got an orthonormal system on the real line. It's got a tridiagonal skew emission differentiation matrix, and the coefficients of the function f. They are Fourier coefficients of some modified function. So some multiplier k and some mapping h, which takes the periodic interval to the real line. Suppose that something like this is possible. Then we could use the FFT to compute coefficients. It doesn't get you anywhere. They're all, the only ones that are of this form are Malmquist-Takarabe. The proof is elementary, but it's just there's nothing deep going on. It's an elementary proof. But it's good to know, sad to know that there is no other family with these nice properties. So if you want to get another basis which you think might be better in some way, you have to break some of these rules. Maybe you will go for quindiagonal. Or maybe you don't let it, it's not orthonormal on the standard inner products. Think of some changes you might want to make it. You're on the lookout for a new basis. Okay, and these Malmquist-Takarabe expansions, how well would it approximate this function? You expect it to be quite good because it's approximating a rational function with with rational functions. And it is, you get exponential convergence. If you make it have slightly different decay at infinity, remember that the Marquis-Sacco functions, they decay like 1 over x in infinity, so a sort of wisdom would say, if you're not matching the decay at infinity, you're going to have a bad time. Only a marginally worse time, it's still the same, it's only a constant worse, it's still 3 to the minus n. These are the modulus of the coefficients. Okay, but what about if we multiply by cos x? Is this going to make the coefficients decay slower? Faster? It's just adding a bit of wiggle to it. It's not done much. Andre knows. It's way worse. It's a smooth entire function, and yet we only get algebraic convergence. So there's some really interesting stuff going on here, which isn't fully understood.
Well, it's not entire at infinity, right? That cos x becomes.
Indeed. But an entire function doesn't need to be entire on the Riemann sphere. But now you're preempting me.
Oh, sorry.
Spoiling the surprise. Imagine the surprise is on this slide anyway. So this theorem, which I'm cheekily attributing to Edelman, just to pander to the organisers, but really it was a theorem of Boyd who alluded to it before Edelman. The coefficients of a Marquis-Sacco expansion are exponentially decaying, which is the ideal situation, if and only if this mild modification can be analytically continued to the complement of 2 disks. So this disk with radius r rho here and center a rho. It's essentially this shaded region here. This is taken from Andre Edelman's paper. But what does this mean? There's a line above the sea. If you want to have exponential convergence, you need to be analytic at infinity. It's super strong. I mean, is the solution to a differential equation going to be analytic at infinity? No, that's a ridiculous thing. So it looks like this is a bad basis to be using for a spectral method. But people have had success, so what's going on? I mean, and the proof of it, I proved it independently myself until I found out that it had not been proved. It's not a difficult theorem. Essentially, the standard theory for convergence of Fourier expansions, you just transplant that theory. So this theory about the radius of the disk for a convergence of Laurent series just converts. Yeah, so it's standard stuff. But what's going on? So Andre Edelman, I keep talking about him. I've probably talked too much about him. I won't say his name again. But he compiled a list of functions that he computed the decay of the coefficients for. And so, for example, a Gaussian it's not analytic at infinity. It's got an essential singularity at infinity, right? And yet, so we know we can't get exponential convergence, but we get sort of 2/3 exponential convergence. And the Sept function, that's not analytic at infinity. It's got an essential singularity again. You get root exponential convergence. So there's some interesting. It's not as simple as the classical case for Fourier series conversion or Chebyshev series conversion. It's a little bit more complicated. But it's an empirical set of results. It's not complete. There's still no comprehensive theory known yet. Okay, so this Gaussian function, these are the expansion coefficients that decay 2/3 exponentially fast. If I shift the function over, this makes it worse because the Marquis-Sacco functions they're concentrated they're centered around 0, and so the functions are relatively flat. The basis function is relatively flat in this area, so they're going to have a bit of a hard time. So for spectral methods, if you're thinking of a traveling wave or something, this will be a real issue. That just simple translation will affect your approximation. This could be remedied by stretching the basis functions, for example. Okay, now we're getting a little bit more interesting. Wave packets. We multiply it by cos 20x. I mean, the previous slide said when we multiply by cos x, it ruins everything. Right? But not for Gauss function. So, Malmquist-Takanaka functions approximate wave packets well. The plot thickens. I should have made the lines in this plot thicker. Just a joke. Okay, so our current work, I've been working with Arya and Karen Long on these wave packets, because there's quite a few papers out there. This is just an example of one. With this is a paper with Christoph as one of the authors. He passed away prior to the submission of the manuscript. But this is them solving nonlinear Schrödinger equation with the Malmquist-Takanaka functions. I want to understand why it works well. This is more of an applied paper, more an experimental paper. Functions of this form, how well does it approximate? This is our current work. Are Malmquist-Takanaka expansions better than Hermite functions at approximating wave packets? You wouldn't think so, because Hermite functions decay like e to the minus x squared. So does a wave packet. It's a good match. But actually, I'll show you the next slide to say there's some evidence that Malmquist-Takanaka is better at approximating wave packets. The number of coefficients for desired accuracy, say you want 10 digits. The number of coefficients you need to take is proportional to the frequency of the wave packet. Something we're trying to prove, but maybe I'll explain that the following slides will elaborate on all these points, and they have question marks to say we've not proved these results yet. We're on the way to. We have some evidence. And if you fix the frequency of a wave packet, you're going to get the convergence that was similar to the Gaussian. There's even more interesting stuff going on. There's interesting transient regimes for the coefficients. So this decay that looks like the decay you get for a Gaussian, it appears to kick in very late, and for small n, there's different behavior. And we believe that steepest descent in the complex plane is the tool to reveal these interesting transient regimes and understand how the coefficients of wave packets behave. Because there's the n variable and the omega variable to play with. Okay. These are errors for approximating a wave packet cos 10x e to the minus x squared using Hermite functions. This is the degree 10 approximation, 40, 70, 100. The errors are going down. You're getting an extra digit also each time. This is 0.001 error there. And these are the Malmquist-Takanaka errors for the same degrees, the same function, but we got 2 more digits for n equals 100. So surprisingly, Malmquist-Takanaka approximates wave functions better. We'd like to prove this sort of thing. We've got a few experiments that show it, but that's one of the things we're looking into. And it's surprising, as I said, because Malmquist-Takanaka, they're rational functions that decay like 1 over x. Wave packets decay much faster than that. Why would they approximate them well? We have some numerical evidence to say that the number of coefficients needed for a given accuracy is proportional to the frequency, omega. So what I've plotted here is various values of omega, the frequency of the wave packet. The blue line is the degree of the number of coefficients for a Malmquist-Takanaka approximation that gets, I think, 14 digits of accuracy. And you see it's linear. And I've plotted in red 65 times the frequency to get extremely high accuracy. And it's all fast to compute as well. You know it's just the FFT. This is numerical evidence, but we want to prove it. And now I'll talk about this transient regime I mentioned. So what I've got here, I've simplified it a little bit. I've modified the wave packet to, it's not a cos omega x, it's an e to the I omega x. So the wave packet itself is the real part. And I'm looking at the coefficients, various frequencies. And it seems that there's a sort of, well, not sort of, but there is a point at which there's a regime change. So if you're looking at omega equals 20, at about, this is about n equals 5, it suddenly changes from this steep curve here to a slow 2/3 exponential decay. And that point at which that changes is actually linear in omega. And it's actually about omega over 4. So if you take n equals omega over 4, that's when you see the decay. So it's not super simple, but with this, the method of CP descent in the complex plane is the only way we know of showing that why these things happen. And I'll explain a bit about that. So this is a super quick guide to steep descent in the complex plane. The concept was invented by Riemann in unpublished notes. A lot of his work was in 1863. So if you have an integral in this form to the hx, where h is an entire function, you can, by Cauchy's theorem, you can deform the contour of integration. So rather than integrating solely along the real line, you're integrating along the contour C. If along that contour there's a point z0 where the derivative of h is 0, then you could do a local Taylor expansion of h on some local region of the curve C0. So you do a local Taylor expansion. The first derivative is 0, so it can be ignored. So then this part is approximate. This first part is a constant that you can pull out. The second part is approximately a Gaussian integral. So with lots of hand waving, locally this integral is well approximated by something that's local to a point in the complex plane z0. And so if you take all the points, if you take some points in the complex plane where the derivative of h is 0, you can add all the contributions up to get an approximation of this form. So what it's saying is that you can approximate this integral with the values using only values of h and h double prime at a finite, well, a discrete set of values, discrete set of points in the complex plane zk. So that's. But it's not clear from this explanation why it's called steepest descent. But this is the gist, that we essentially want to find these what are called saddle points. Find where the derivative is 0 of h. Okay, so for our problem, this is the Malmquist-Takanaka coefficient of a complex wave packet. If you set it to exponentials and logarithms, you can express that as an exponential of a function h, which is this form, which is n log 1 minus 2iz, which comes from this guy. N plus 1 log 1 plus 2iz comes from this guy on the bottom. Look at the derivative, and the zeros are the zeros of a cubic. So this is probably one of the nicest situations you could have for steepest descent, where actually we have exact solutions for where the stationary points are. So there are 3 points in the complex plane always. So this is a diagram of where the stationary points are, and the contour of integration that's been deformed follows paths along this, passing through the stationary points. But of course, there are 2 parameters, n and omega, in these points. So what's plotted here is where those stationary points go in the complex plane. So this is for a fixed omega and n increasing, just as an example. But the interesting thing is that we can see exactly when all three roots cluster around the imaginary axis. And so we can, I'm not going into too much detail, but where these stationary points coalesce on the imaginary axis is where that turning point was on this graph. So this line, which is approximately n equals omega over 4, is predicted by when these stationary points reach the imaginary axis. So the steepest descent in the complex plane is explaining something which is purely an approximation phenomenon on the real line. It's one of those nice justifications of complex analysis, where the shortest path between two truths on the real line often passes through the complex plane. How these three babies dance across the complex plane tells you these kinks in the coefficients. So it's interesting analysis going on, which we don't fully understand. But the point I want to say is that the steepest descent approximation that I mentioned, which is the sum of these over the stationary points, it actually gives a good approximation to the coefficients. The blue is the coefficients of this complex wave packet, and the estimate derived from steepest descent is this red line, which matches it exactly. And this N2 here is where the stationary point reaches the imaginary axis. I have to give credit to Karen Lung for this discovery of this critical point. But for the moment, so this plot shows that the steepest descent approximation is valid. It can be used. So our current work is understanding how these guys behave with respect to n and omega. But at least we're dealing with values of a function at a point rather than an integral. So stay tuned. Hopefully I'll be able to talk about this in December and have some even more beautiful complex analysis. Okay, so I've still got time. So my last bit, which was optional, is coming. So this is now nothing to do with Malkuth-Takanaka, except that I have written MT for Malkuth-Takanaka on the slide. But let's try and find another family of polynomials which is a candidate for a spectral method on the real line. So the Malkuth-Takanaka functions, they have this property that their expansion coefficients were Fourier coefficients for a modified function. We like orthogonal polynomials. Why don't we do an orthogonal polynomial version? So let's look for functions which are orthonormal on the real line. Let's make some assumptions that it's a real skew-symmetric differentiation relation. Let's try diagonal. And these functions are a weight function theta times by an orthogonal polynomial Pm. Maybe I should have called that Qm, because this has nothing to do with the Pm's in the previous theorem. A map H, which takes the real line to the interval -1, 1, with some weak assumptions. They're incredibly weak. Technical. If you're looking at functions of this form, then the expansion coefficients, because it's an orthonormal basis, remember the expansion coefficients in this basis of a function f. If you do the change of variables corresponding to h, then the coefficients they're not Fourier coefficients, they're orthogonal polynomial coefficients. These orthogonal polynomials Pn. So if you wanted to compute the coefficients of such a system, you would do so by computing this modification and finding the orthogonal polynomial coefficients. And these might be too stringent conditions, but it turns out they're not. What we managed to prove was that the only systems with these properties, normal, tridiagonals, skew-symmetric differentiation matrix, coefficients are orthogonal polynomial coefficients, only systems with those properties are this form. So there are some polynomials here, Pn alpha beta. These are the normalized Jacobi polynomials. And they become functions on the real line via the tangent map. And then you pre-multiply by this weight. And these functions, they have the nice differentiation matrix. They're all normal. But furthermore, the polynomials that actually ended up popping up out of nowhere. It would have been nice to talk about the proof a little bit. It's an elementary proof, just like this. It's an elementary proof, but the Jacobi polynomials just pop up out of nowhere. Because we just said any arbitrary orthogonal polynomial system on -1, 1. But the Jacobi polynomials just pop up. They're the only ones that can satisfy all the constraints. And we're very surprised it's not some esoteric, crazy polynomial family. It's the Jacobi polynomials. And we have fast transform methods. We can compute coefficients in that basis really fast using FFT-based algorithms. So this basis you can compute coefficients very fast, which makes it scalable. Just let's pick alpha is -1/2, beta is -1/2. That gives what we will call the Tanch-Chebyshev functions. And this is a portrait of Tanch-Chebyshev T, Tanch-Legendre, so alpha equals beta equals 0. Tanch-Chebyshev U. These are some interesting functions which you might consider using for a spectral method, but we have not done anything. We just found them, wrote them down, not a chance to work on them anymore. But remember that the first theorem that I showed was that all systems with tridiagonal skew emission differentiation, which is that they're Fourier transforms of some weighted orthogonal polynomials. So these guys are these tangent-Jacobi functions. They are Fourier transforms of these weighted orthogonal polynomials. So these are polynomials orthogonal with respect to this weird weight. Now we're straying into the complex plane again, which is nice. So there's a duality between these two different families of orthogonal polynomials, Jacobi polynomials and then orthogonal polynomials on the real line, which are traversing the gamma function in the complex plane. And because this weight function decays exponentially, it means that you get completeness. So what these orthogonal polynomials are, these look weird. We've strayed into the complex plane. This is the weight function we're looking at. What it's doing is this is a plot of the gamma function, and it's going. This is a real argument, alpha plus 1/2, and this is going up into the complex plane. So we're essentially looking along these lines, and we're getting weight functions which look like this. These are unusual weights to be considering orthogonal polynomials for. But if you set alpha equals minus beta, you get a family which is known called the Karlitz polynomials. But for general alpha and beta, these Karlitz polynomials, they're in Chihara's orthogonal polynomials book, for example. And we've got some orthogonal polynomials experts in the room. I hope I have something to say about this. This appears to generalize Karlitz polynomials. I don't know what it means, but
for beta equals minus alpha, it's 1/cos squared.
Exactly.
Yeah, so
that's
you
that.
have this hyperbolic substitution, so you go back and you probably recalculate. No.
Yeah, so that's familiar form of the Karlitz polynomials. So that they're not usually thought of in terms of gamma functions. Another aside, actually, is that this equation here is a generalization of a result of Ramanujan. Where his version has n equals 0 and alpha equals beta. It's nice to generalize results of Ramanujan. It's something on the bucket list. Yeah, we're straight into the complex plane. Don't know what it means, but there it is. Don't know anything about these polynomials really. Okay, this is the outline and the outlook. Spectral methods with skew Hermitian differentiation matrices are stable by design, as Isel has puts it in an earlier paper, and they're energy preserving, the energy being the L2 norm, by design. Now, and one of our first theorems was we characterize all systems on the real line with tridiagonal skew emission differentiation matrices. And these were Fourier transforms of weighted orthonormal polynomials. And it was very easy to find the constraints that made it an orthogonal system. Along the way, we rediscovered the Malthus-Takanaka functions. And the current work is straying into the complex plane. We're trying to understand the approximation theory of these Malthus-Takanaka functions, building on the work that's already been done. And we think steepest descent in the complex plane is a promising approach. Also, in another paper, we discovered Tanch-Jacobi bases. I don't know if discovered is the right word. I mean, anyone could have written them down but not known the relevance. That they would have tridiagonal skew symmetric differentiation matrices. And these are orthogonal polynomial versions of Malthus-Takanaka. So that's all I have to say. Thank you for your attention.
Questions?
Can you say anything about how the hyperbolic Tanch-Jacobi bases compare to the empty functions in terms of approximation?
Well, one thing that is surprisingly similar is that the interpretation that we arrived at Tanch-Jacobi functions was through a mapping H. We said we're going to map from the real line to an interval and use orthogonal polynomials on that interval. That's the Tanch map. Then what we found for Malthus-Takanaka is they have a similar property. They're mapping the real line to an interval, but via, well, where is it? It's actually an inverse Tanch map. So inverse tan and Tanch behave very similar. The one's a periodic version of the other. So the key relation was like the derivative of Tanch is 1 minus Tanch squared. This relation, that was key in the relation to make it all work. But that's the main similarity between them. Otherwise, they can't be that similar because Malthus-Takanaka, they are meromorphic functions, but these Tanch-Jacobi, they have a Tanch makes it have an essential singularity in infinity. So I think the approximation theory of if there was to be something that united them both, would have to discuss this singularity in infinity. We don't know much about it.
In that direction, I was thinking what parametric families might be most useful for convergence studies. And the one that occurred to me, based on your early examples, would be something like x to the minus alpha, e to the minus beta, say mod x to the gamma. So for that one, do you know the convergence rate as a function of alpha, beta, and gamma? Because it just seemed to encompass the large mod x behavior for one or two of your examples.
So do you mean that this is parameterizing the orthonormal polynomials that we take the Fourier transform?
The function you're going to apply your method to.
Yes, we in the first paper we did study Freud polynomials. I didn't quite pass the weight that you were mentioning. Was it essentially a Freud weight, or didn't?
It wasn't really the weight. It was just
He's talking about a model function.
a model function.
A model
to see
function
how
for
rapid.
analyzing the error.
So
Oh,
because you gave various examples where the result was not what you expected.
Yeah,
I'm
yeah.
just saying a simple example that occurs to me.
okay.
Concentrating on the large x behavior would be something like x to the minus alpha, e to the minus beta, say x to the gamma,
Yes.
or mod x, yeah. And then the obvious question is, what's the convergence rate as a function of a, beta, and gamma?
Yeah.
That might be obvious, you may have done it, but it just struck me that was the large mod x behaviour
Yeah.
of several of your examples. Anyway, just one.
No, that's interesting.
This is, it is quite interesting because this is actually a very good model. But tell it to an approximation theorist, and I'm one.
Yeah.
And at the first moment, they will be absolutely horrified. Because in a finite interval, the theory is known for 100 years, goes back to the work of Bernstein in 1910s, 20s. And we know exactly that if you have an analytic orthonormal basis, you approximate an analytic function, and both the functions you are approximating, the analytic function, can be extended a little bit into complex plane, then you have geometric decay, and you can determine exactly the rate of decay. And all this is known. And then you can go into more complicated classes, Sobolev classes, and things like that. But actually, this breaks down on the real line.
It's this behavior at infinity.
Yeah, exactly, because the
It's
behavior
the
of
new
infinity.
ingredient.
So things like this might be very, very highly relevant.
So we think we have some control over how this essential singularity behaves.
But in classical Fourier theory, there's this table in Lighthill's early book, which gives the limiting behaviour for a very wide set of parametric families. And in certain parts of wave theory, this table is kind of burned on our minds because we use it all the time in asymptotic theory. But anyway, perhaps at some later stage I can show you that
But
table.
that gamma,
Yeah.
what does it actually add? If you just make a substitution next to the gamma as tau, then you change alpha, and you come back to the original integral. So what is gamma?
So there's probably some redundancy between these three variables.
Yeah, but then you of course alpha and gamma. I mean, one of the parameters is gone, and I have again two parameters, alpha and beta. And we play with them.
But it's something about the essential singularity of infinity and about the directions in which you could approach it, perhaps. That's what this would be controlling. Controlling where the path of deepest descent might go. We don't know.
Are there useful collocation formulations of these spectral methods?
Collocation formulations.
But the unknowns are the pointwise values of the function rather than the expectation coefficients.
You just make the tan half theta transformation and you do things in Fourier, differentiate using function values.
I think we don't have the faintest idea, and I can tell you why.
Glad you said it.
No. I can tell you why. So the reason collocation works so well in a bounded interval is because Lebesgue constants of L2 approximation, like Fourier or orthogonal polynomials, and of collocation are within almost the same. So collocation is slightly smaller, but it is by something like 2 over pi over 2, something like this, larger than. So using collocation is just as good as using the best approximation. But on the real line, we don't have the faintest idea. The whole theory has to be developed essentially from scratch.
But in practice you can do it because
Yes, in practice, I'm sure.
if you have the u by the x on the real line, you set x equal to half tan, half theta, you convert it into theta,
Yeah, of course.
it becomes a function now with non-constant coefficients, but collocation like it doesn't care.
Is the skew symmetry of the differentiation matrix preserved in that case?
That we'll have to think about.
Not necessarily. So I can tell you one sort of example, and this is different work of Carolina and myself and Bernard Singh. So if you are using Fourier expansion, sort of Fourier basis with periodic boundary conditions to solve the linear Schrödinger equation, then you obtain a diagonal skew Hermitian diagonal differentiation matrix, but the potential, the interaction potential, is is a Teplitz matrix, so periodic Teplitz matrix. If you are doing collocation, it is the other way around. the differentiation matrix is periodic templates, a circulant, and the potential is diagonal, which is excellent news because you can evaluate the exact exponential of either collocation circulant or diagonal matrix very, very rapidly.
So this could be done with these spectral methods where if you do an operator splitting, where you're splitting the derivative parts, where you've got your derivative is going to be a tridiagonal matrix, which perhaps you could make good methods for. Then the variable coefficient matrices you could do in collocation space, and that's diagonal, just like the Fourier case, utilizing a fast transform.
We should probably stop. We're already 5 minutes past 10. So let's thank the speaker.